Definitely more fun.
It's good you waited, or you did it before class.
Yeah, before I started.
No quiet waiting. Yeah.
Yeah, it happens with my siblings.
So, I'm sorry, I was like,
Yeah, just
Okay, so today I'll have my office hour as always after class outside over here. If there's a table open, it'll be beyond the bushes over by the tables. I was just alerted to the fact that the question number 3 in the problem set might not have the equation that you need listed on the list of equations, so I'm going to look into that, and I'll send an announcement about that as soon as I get to the bottom of that one. And with that, we'll proceed with the lecture material. So we're going to, today and on Friday, finish up our lectures on fluid dynamics. And that discussion has revolved around the fact that the drag in air under airflow is greater for a sphere than a streamlined body, but then when you put them in glycerin, you get exactly the opposite result. And we've considered models for how drag is generated by skin friction when viscosity is dominant, and versus generating drag through pressure differences along a body. And we have the model for that form of drag shown right here. So the question at the moment is, well, how can we calculate which force matters? If both of these forces, every fluid has a density, it has a viscosity, how are we to know when one force matters and the other one doesn't? And to answer that question last time, we presented this notion of just taking the ratio of the two forces, and if the denominator, that's the skin friction force, is bigger than the pressure drag force, then this ratio should be much less than 1. Whereas if it's much greater than 1, then that's suggesting that pressure drag is much greater than skin friction. And this, by the way, applies not just to drag. You know, drag is just the force that points in the direction of velocity, but it applies to thrust and it applies to lift and really any fluid dynamic phenomenon. This ratio is kind of like a magic number. And why did we do that? Oh, okay, we broke it down into that final version. And we now know that that's called the Reynolds number. And so the Reynolds number provides us with a metric of the relative magnitude of inertial forces. Those are the ones generated by pressure, and the viscous forces, those that are generated by viscosity. So this lecture, which is going to be done like halfway through the class period, is about Reynolds number. And so I want us to sort of think a little bit more intuitively. We've sort of considered some math, and now we're going to see some flow visualization examples with another one of our old school film clips.
Can give us such an insight. In defining Reynolds number, the appropriate length and velocity to be used are the diameter and the velocity of the jet as it enters the fluid. Here the fluid is syrup, and the Reynolds number is 0.05. At this low Reynolds number, the jet hardly penetrates at all. Now let's repeat the experiment using different fluids. The other three boxes contain glycerine, glycerine and water. Each jet will be driven by this piston, and the velocities will be identical. This glycerine jet penetrates to a depth of a few diameters. At this Reynolds number, the jet penetrates many diameters. The tangential force acting on the outer surface of the jet is insufficient to reduce its velocity very much before it reaches the bottom of the box. This jet becomes turbulent here. For comparison are the four situations.
Okay, so you can see that at the higher Reynolds numbers, you have a wake that's turbulent and much less orderly than at the lower Reynolds numbers. And one thing that's kind of, our focus has been on forces and what generates drag in particular. But one of the things that's kind of neat about people who are interested in fluid dynamics or biofluid dynamics is there's a bit of a what you see is what you get phenomena. So the pressures that generate forces and the shear stresses that generate forces can be visualized, and you can directly infer forces from visualizations. So these are not just pretty pictures, but they also, these kinds of images can be used to get insight into the forces that are generated. All right, so here's another property at those low Reynolds numbers when viscosity is dominant.
Low Reynolds number flows are reversible when the direction of motion of the boundaries which gave rise to the flow is reversed. This may lead to some surprising situations which might almost make one believe that the fluid has a memory of its own. Here are two concentric cylinders. The fluid can be moved by turning the inner cylinder with this handle. The annulus between them is filled with glycerine. Into this space I introduce some dye, which stays put owing to the high viscosity of the glycerine. Note its position before I start turning it. I now turn it 4 times, pushing the handle clockwise. The dye seems to mix as a drop of milk mixes when it is stirred into a cup of tea.
Very British.
Now I reverse the direction. And after turning exactly 4 turns, the dyed area reappears in its original position, with a little fuzziness due to molecular diffusion. To see what happens, we have a second apparatus that is filled with syrup. It has a wider gap, and we can look down on it. A little coloured syrup is injected to mark the fluid. When the cylinder is turned, this fluid is stretched round the annulus. Now the inner cylinder is turned back exactly to its starting position. During the forward motion, the boundary of the fluid follows a path determined at each instant by the motion of the ball. At these very low Reynolds numbers, particles within the fluid move when the boundary moves, and they stop when it stops. During the reversed motion, the boundary of the fluid position.
Okay, so that clip was, just as a small historical footnote, that was James Lighthill, who was a famous aeronautical engineer, but he also dabbled in biology. He was also a bit of a wild man. He doesn't look like it, but he was really into swimming, and he would do these like epic swims, and he passed away swimming across the English Channel. It's tragic, but he was doing what he loved. Okay, so anyway, this tradition of visualizing flow and making inferences about fluid dynamic forces was part of the story about the discovery of Reynolds number. So we talked about Reynolds number in the context of trying to figure out which forces matter with respect to drag, but it was originally discovered by visualizing turbulence. That is the presence of turbulence. And there was something that Reynolds, Osborne Reynolds, who's shown here, this is a figure in the original study. This is like, in the 19th century, people would draw self-portraits in the figures of their papers, which is kind of a funny tradition. And he was, a snappy dresser. And what he noticed was that flow in a channel at a certain point can become turbulent if you change the right parameters in this situation. And so somebody recreated Reynolds' original experiment. So what this is up there is the surface of a glass tube, and you have something else down below. And then in the middle, that line is a stream of ink. And the way these experiments work is there's essentially a fish tank here, but it has a valve that is a little hard to see, but the valve just spills the water on the floor, and up here is a handle so you can control the rate of flow out of that valve. That pipe is connected to this funnel here. So what it does is it sucks in the water, it draws it through the pipe, which you see here, and then he has this little trail of ink in the middle. And in this particular situation, so water is flowing, and what you can see is that the water is so aligned that the ink line in the center is just a totally straight line. But as he began to change variables like the speed of flow through that pipe, then at a certain point, that line of ink starts to get a little wavy, and then it starts to get really messy, and then it just becomes a total mess. And that's because the flow is becoming increasingly turbulent. Now, the opposite end of this spectrum is something we call laminar. Laminar flow is when all of the fluid is moving in unison. It's all got a velocity pointed in the same parallel direction, and it's equal in speed. And, well, I should say it's pointing in the same direction. It's not necessarily equal in speed because, as we know, the viscosity of the fluid is going to cause some layer of the fluid, in this case water, to stick to the surface of the pipe. But despite being a little bit slower than the flow in the center, it's all pointed the same way. And so with this apparatus, what Osborne Reynolds did was to vary different parameters that he could think of. Like, well, what if the fluid is a different density? And what if I add sugar into the water to make it more viscous? And if I can quantify those factors, then I can see how they might contribute to this propensity of the fluid to go from laminar to turbulent. And he focused in on a particular level of turbulence, maybe like this level, where it just kind of starts to look like something different is happening. And so he would progressively increase the speed, increase the pipe diameter of this glass tube, and he would increase the density, increase the viscosity. And so systematically, he began to decode what it takes to cause the flow to become turbulent. And so he empirically, instead of like what we did, where we already knew some of the governing equations, this was at a time when those weren't necessarily clear, and Reynolds was an empiricist, and so he just pursued it experimentally. And so, so one thing about the Reynolds number is that any combination of these parameters, so long as it gets you to the same Reynolds number, will generate flow that looks the same. So you can increase the speed, and at a certain point you get to a Reynolds number where it becomes turbulent. Or you can increase the diameter. It's an either or situation. It doesn't matter which parameters you change in order to get to the same Reynolds number. So the stuff in the numerator would tend in these experiments to increase turbulence, versus the viscosity will tend to decrease the turbulence. And he discovered that this sort of magic ratio at a certain value of the Reynolds number will create a turbulent flow. Okay, and this range of Reynolds numbers. So here, the particular length that's being used, before we were talking about like an animal's body length or something like that. For flow through a pipe, you use the diameter. So to use sort of generic language, this L is called the characteristic length, and it tends to be in a particular body of literature that there's some convention. So, you know, people who study flow through pipes, that would always use the diameter. People who study swimming fish always use the body length. So everybody sort of agrees, like, this is the length we're going to use. And again, Reynolds number is only really meaningful over orders of magnitude, and it's a little arbitrary which particular length you choose, so long as you're consistent, so that you can make comparisons across those Reynolds numbers. Okay, and as we've already discussed, it approximates the inertial, that is the pressure-generated forces, over the viscous forces. Now, when you apply this principle to biology, you see it reflected in all different kinds of phenomena, and people often use it to think about locomotion. You can sort of see a little bit of the wake of an eel swimming across the screen, and it has a very similar waveform as something like a spermatozoan, even though it just looks different. You know, the way that these animals are moving, or parts of animals are moving, they're moving in a, you know, it looks like they're swimming in a gelatin versus what you see in the eel, and that's by virtue of them being operating at very different Reynolds numbers. So if your Reynolds number is roughly above 1,000, most of the drag, most of the thrust, most of the lift is going to be generated by pressure differences on the surfaces of the animal, whereas a microorganism is going to be just dominated by the viscous forces that are generated by the fluid. And just to give you a sense of some values that are used, so again, our focus is on orders of magnitude. So here we have the flow from laminar to turbulent, but that also corresponds to viscous forces dominating. In the case, again, doesn't have to be drag, could be thrust, etc. Viscous to inertially dominated forces. So as you might expect, a whale is going to have pretty big Reynolds number. They're big in length, they're big in speed, and then that's about all that matters because the water has a fixed density, a fixed viscosity. That is the same water that a bacterium is swimming through. And you can see its Reynolds number is, a teeny tiny number because the viscous forces are much greater than the inertial forces. And then in between, you might have a combination. And so, for example, for a fruit fly, you can see real viscous effects to how they move when you visualize the flow over a fruit fly wing. It really looks pretty sticky. You got kind of a thick boundary layer, and it looks like they're kind of swimming in honey. Even though it's air. And so there you have the opportunity both for viscous forces to influence the flow, but pressures are dominant as well. Okay, so one really neat feature of Reynolds number and studying Reynolds numbers is that since the flows are similar, irrespective of how you achieve a certain Reynolds number, then you can play with that as an experimentalist. And so this is what we call dynamically scaled models. Dynamically scaled models, what that means is, for example, you can take a model of an airplane and put it in a wind tunnel, and you can study its ability to generate lift and the drag on the hull, the fuselage. You can study these phenomena despite the fact that your model is smaller than an actual airplane, so long as you achieve the same Reynolds number. So let's just think about that. So if I want the Reynolds number to be the same and my fluid is the same, so I've got the same density and the same viscosity, because after all, this is a wind tunnel, then the only two variables left are the speed and the length. So airplanes are both big and fast. So if I want to have the same Reynolds number with a smaller length, that means I need to crank up my wind tunnel to a faster speed by the same amount. So if I'm halving the size of the plane, I have to double the speed. If it's a quarter the length, then I gotta do 4 times the speed. So, wait, did I say that right? So if it's half the length, I have to double the speed. Yeah. So that means wind tunnels have to be really, really fast if you're going to have a model that is significantly smaller than the actual airplane. And so these folks wouldn't want to stay in the wind tunnel when they actually turn it on because it's a quite fast flow. Now, what might they measure? Well, you want to measure force coefficients because here, for example, we have the drag equation, okay? And we know that this is the high Reynolds number drag equation, and we know that drag is going to vary with the square of speed. And so if we're putting our airplane in a different speed from the real airplane, then the magnitude of the drag force is going to be different because we're giving it a different speed. But what we can do is we can rearrange this equation and solve for the drag coefficient. If you're replicating the realistic Reynolds number, then the drag coefficient will be the same. If it's the real airplane, little airplane, drag coefficient's the same. Because we're essentially correcting for all of the differences. So we take our measurement of the drag force and we're correcting for density, well, density is fixed. We're correcting for differences in the area, for differences in the speed. So the drag coefficient can be measured in a dynamically scaled model provided you're replicating that same Reynolds number. Is anybody confused about that? So you essentially, you're after force coefficients, because ultimately that's what we want to know, like what wing shape generates high lift. And given that the interactions between a turbulent airflow and a shape are so complicated, this is still, even in this day and age, a very empirically driven field. You can do computational fluid dynamics to replicate these situations. Sometimes that's a little bit quicker and easier. But that approach only works at high-ish Reynolds numbers, usually not the Reynolds numbers of airplanes. And so if you want to know the lift coefficient, the drag coefficient of a shape, because those are the shape properties, then this is what you have to do. Now, biologists have taken advantage of this, and there's a big area of literature in animal locomotion that's concerned with insect flight. So there's a lot of insects, that's one reason. But the other is that this sort of standard conventional equations for describing fluid forces, so, for example, the drag coefficient, or the drag equation, I mean. If you take the drag equation and you apply it to an insect wing, then basically that kind of approach does not explain how animals can stay aloft, how they generate enough lift in order to fly. So I'm glossing over some of the details there, but the idea is that basically this sort of wind tunnel approach to understanding fluid dynamics does not work for insect wings. And so, so this is RoboFly. So RoboFly was developed about 20 or a little bit over 20 years ago. And what it's doing is basically taking this principle. So we're replicating an insect wing. We're moving it with the same motion that we can measure in a real insect. And we're instrumenting it with force devices that allow us to measure forces in 3 dimensions. And this whole structure is immersed in a fluid that is not air, because the wing is like about this big. So if we want our Reynolds number to be the same, we've got a bigger L than the real insect wing. So we have to vary the other parameters in order to get the Reynolds number to be the same. So one thing is that it's moving more slowly, at least rotationally, so you can decrease your U compared to the real insect wing to compensate for that larger L. But another thing is that you can increase the viscosity of the fluid in order to compensate for that big L, in order, again, to get the same Reynolds number as a real insect wing. So this whole device is immersed in mineral oil. Mineral oil, it turns out, is not electrically conductive, so you can have all of your electronics just exposed to the mineral oil, which is a neat trick. And you get really clean force measurements. So you can get your lift and drag coefficients for a wing just by replicating the motion and the shape of an insect wing that's immersed in mineral oil. So in some cases, you can just use a rigid body, stick it in the kind of flow that you might encounter, be it an airplane or some animal, like a bird gliding, that sort of thing. And then other times you might want a more sophisticated robotic approach where you're actuating it in this sort of complicated way. Any questions about that? Okay, so let's move on to the next fluidsy topic, which is lift. Okay, so here we've got, instead of a tuna, we have a vulture, I think, gliding bird in flight. We have a flow velocity to the right because it's moving with some velocity to the left. It's got a weight, and in order to offset that weight, it generates lift. Now, lift, like drag, is defined with respect to velocity. So instead of being in the direction of velocity, it's perpendicular to flow, to that velocity. And the lift equation is essentially the same as the drag equation. It's just that we're applying that same equation to force pointed upwards. So for really small critters in water, they don't generate lift. So lift is only, lift does not emerge from viscous forces. It only generates from pressure forces. Viscosity can influence the flow and indirectly influence lift, but lift only uses this high Reynolds number equation. So we don't have like a viscous dominated version. You can see there's no viscosity in that equation. Density is all that matters. Okay, and I think, you know, folks probably have heard of lifts. You know, it's what allows airplanes to stay in the air. But let's think about it a little bit. Now that we have a foundation and some of the basics of fluid dynamics, let's think about it a little bit more explicitly. Like, how is it that lift is generated in particular? And how can the shape of a wing change the lift that it generates? So we've already talked about this. So what we've established at high Reynolds numbers, where pressures really dominate, is that the streamlines that you might look at over an airfoil can be used to infer the flow speed. And because of Bernoulli's law, we know that the flow speed directly affects its kinetic energy, and that kinetic energy is reflected in the pressure. So in particular, because Bernoulli's law is a conservation law, that when the kinetic energy goes up, the pressure goes down. Okay, so high speed corresponds to low pressure. And they're so explicitly related that we can just take the kinetic energy of the fluid in place of the pressure that we care about. And if we take that expression and integrate it over the whole surface area, multiply it by little patches of area, then that's how we arrived at the drag equation. All right, so we can take that principle and apply it to a consideration of lift. And for that consideration, instead of looking here on the right, what I've done is to draw all the pressure forces on the lower surface in blue. And then on the top surface, we have those pressure forces in green. And here we can see that they're overlaid perfectly on each other because there's no reason to think that it's not symmetrical, that you have exactly the same forces acting on both surfaces because the flow is the same around it, provided the body is pointed directly at the flow. If we chop it in half, we've got a different situation. So we have the same flow over the top surface. We have all the green vectors there. But the flow down below, basically, especially if we ignore viscosity, basically it's all the same velocity and therefore generates the same level of pressure. And that pressure is like somewhere in between the maximum and minimum values that we see in green. All right, so what we've got here is a pressure imbalance. The flow on the top surface, sorry, it's hard to see my pointer. On the top surface, maybe we could zoom in. Okay, so on the top surface, you have that bottleneck. The streamlines get slimmer, and that means because of continuity, the flow speed is greater. And because of Bernoulli's, that means the low pressure. We've got that up top, and then we have an increase in pressure as the fluid slows down. Down below, none of that happens, okay? You've just got the same velocity, it's the same intermediate velocity as you go down the length. And because that pressure, the corresponding pressure, so again, think of that velocity being relatively low. So that means the pressure is going to be relatively high, according to Bernoulli's law. And as a consequence, you have kind of more of a push upwards than you do from the green vectors pushing downwards. And so if you were to, again, integrate over the entire surface, all the little forces that are generated on little patches of area, then you would have a net force that points upwards. Okay, now the component of that force that is vertical, so again, lift is defined, as perpendicular to velocity. And since the free stream is horizontally oriented, then we have to define lift as the vertical component of that force. So we get a pressure-generated force, the vertical component of which is lift. So the net force is mostly lift. And for simple geometries, and when the geometry is pointed very close to being in the direction of the flow, you often just assume that that force is totally equivalent to lift. And in that particular case, it looks pretty darn close. Okay, so we can do the same math as we did for drag. So if we're interested in pressures, we can integrate them over the surface. But if we, instead of pressure measurements, if we instead have velocity measurements, again, we can just plug in for pressure the kinetic energy of the fluid. And as long as we can measure the velocity, then we can calculate lift from just figuring out what u is everywhere down the surface. Okay, and if you do that integration, you end up with, like I said, exactly the same equation. It's just that the integration constant we call the lift coefficient in this case. And so we said that the drag coefficient is indicating the dragginess of a body. It's the aspect of the equation that gets into shape. Lift is the same deal. It's just that it's essentially the liftiness of a shape, the propensity of a particular geometry to generate a lift force. So the bottom line here is that lift is generated by an asymmetry in flow. And what I mean is like the top surface compared to the bottom surface. So this can be done through geometry. It can also be done by tilting the geometry with respect to flow. So much like your hand sticking out the car window, if you have a flat orientation, then you don't feel much of an upwards pull on your hand. But as soon as you tilt your hand up a little bit, now you feel it. Okay, that's lift, or mostly lift. And so you can experiment, as you probably have, you can experiment with how the orientation, so same geometry, but I'm just changing the orientation of my hand, and that has a big effect on the generation of lift. So we got another film clip for that.
The average speed above the airfoil is approximately the same as beneath it. When the airfoil is set at angles which give large lift, the portion of the timeline passing above the airfoil outruns the portion beneath. The velocity is higher near the upper surface. At negative incidence, the effects are reversed.
You can see the boundary layer in that for boundary layer fans. Like right there, that change in shape is partially a function of the viscosity on the surface. But you can really see how, like in the trailing edge, like these strips of fluid have moved much faster than the ones up top. Let's see, I have another clip in here. I think it's just, yeah, so we're just showing what happens to these streamlines as the angle of attack increases, like that. And you can see that it starts to get really turbulent sometimes and actually unstable. So we'll take that movie and draw streamlines. And let's just consider. So, in the first case, we presented an asymmetrical shape to create an asymmetry in flow, which generated lift. But here we have a symmetrical shape that we're just tilting. And what happens is that, again, just like the asymmetrical shape, we're creating a bottleneck in the flow as seen by the streamlines over the top surface. So you have a slimming of this region up top that is not reflected by what happens down below. And as a consequence of that slimming of the flow, again, it's as if a pipe is smaller in its diameter, then the flow speed goes up, and because of Bernoulli's law, the pressure goes down. And you apply that kind of logic to flow all the way down the top surface, and you see that the pressure is low, then it gets slightly higher and slightly higher. And again, the forces generated are always normal to the surface. So they do have this kind of angle, which is just a function of the shape relative to the flow. So we see that there's a forward component to that force. So there's actually a little bit of thrust generated by that force vector. And then the vertical component would contribute to lift generation. And down below, where you have a relatively low speed by comparison. You don't have this whipping around of flow on the top surface. Instead, the flow stays relatively low, and you have higher pressure as a consequence of that. So again, there's an imbalance. This time the asymmetry is just created by tilting the structure instead of changing its shape. So you get a net force that's upwards and describes mostly lift, but there's also a little bit of drag. And so, one thing, you put your hand out the car window, if you increase this angle a lot, it's called the angle of attack. If you increase it by a lot, then you start to feel your hand pulled backwards. And this is like a 90-degree angle of attack. It's just all backwards. That's drag, right? Because that's the force that's in the direction of flow. So you're feeling all drag in that case. Versus this kind of angle, you're feeling a lot of upwards force. So the force is just pressures and pressure distributions. But because of our convention of naming the forces with respect to the direction of flow, you have a little bit of drag at a little of an angle of attack, the induced drag, and then you get a lot of that force if you keep tilting. So here we see the angle of attack is conventionally done as alpha. Angle of attack is something that's often varied in these wind tunnel experiments. You can change the angle of the whole airplane or maybe just the orientation of the wings as they're fixed to the airplane. And just like you can measure the drag coefficient, you can also measure the lift coefficient. So again, lift and drag coefficients tend to indicate the dragginess of our geometry, and that includes changing the orientation of the geometry with respect to flow. So here we see measurements of the lift and drag coefficients. And these work for any particular flow speed. You would just take your measurement of the drag coefficient, lift coefficient, and plug them into the lift and drag equations if you wanted to know what the explicit force was, like in newtons. But on the graph, we can see that it's just done as these non-dimensional quantities. And this is just an example. There's lots of studies that are like this, varying the angle of attack. I'm not sure. Okay, so down below are drag coefficient values, and then these are lift coefficient values up top, the big ones. And this is like a review from a number of studies. And what it shows is that as you increase the angle of attack, so these are really small angles, so we're only up to 18 degrees, pretty small angle, which is typical for airplanes to stay at those low angles. You can see that the lift coefficient goes way, way up. It's very sensitive. And then you only get a slight increase in the induced drag. And that's just because of what we see over here. We've got this big vector mostly pointing upwards and just a little bit pointing backwards in the direction of flow. Okay, now there's a phenomenon that occurs when you sort of take this too far. You might think like, oh, okay, angle of attack going up, more lift, that's a good thing. Let's do more of that. Let's have an even greater angle of attack. But what you can see here is that there begins to be a drop-off in the lift that you get. There are diminishing returns on what you can squeeze out of a wing by increasing its angle of attack. Does anybody know what that phenomenon is called? It's when, what's that?
Stall.
Stall, yeah, very good, thanks. Yeah, so stall is a loss of lift at high angles of attack. So this can happen to airplanes. They can fall out of the sky catastrophically if they have too high an angle of attack. And in fact, the 737 MAX is partially a stall issue. That story with respect to that airplane model. It had to do with the control of the angle of attack, and there were a couple of crashes, unfortunately, related to basically the airplane achieving too high of an angle of attack and then creating a catastrophic lift problem. And we saw that kind of situation in this film clip where as you increase the angle of attack, they're going way beyond this 18 degrees here. And what you can see is in the top surface of the wing, this is a very high Reynolds number situation. It's very turbulent. And that instability created in the flow on the top surface essentially creates these oscillations in lift that really sort of throw the whole balance out of whack for the airplane. So the instability can make it difficult for the airplane to recover in terms of the direction that it's going in. Okay, so these principles, this basic approach of you replicate the Reynolds number, you stick some biological structure into a wind tunnel, you measure force coefficients. This is the approach that I was referring to when I said that we don't have, traditionally, we don't have a great understanding for how insects fly because this is essentially what was done for insects. So here, for example, is a study done where this is an insect wing, the test object, and it's hooked up to a beam, and they calibrated, like a piece of metal, they calibrated that beam for its force by hanging weights off of it, getting a relationship between how much force it takes to deflect it a certain amount. And what they have up here is a photodiode that lets them measure how much this piece of metal has deflected when the test object is exposed to flow. And they did it in 2 dimensions. It's kind of neat. So they have a little LED on one side that generates the light, and then on the other side is the sensor, and in the middle is that piece of metal. And as it moves around, it changes, it casts a shadow from the LED light onto the sensor, and that allowed them to measure how much the beam was deflecting, and therefore how much force was generated on the little wing as they pass flow over the wing. So they're taking actual insect wings, these are not scaled models, and measuring the forces on those wings. And again, they get the same kind of measurements. So here, instead of angle of attack, you have the drag coefficient plotted against the lift coefficient, and the numbers here are the angle of attack. So a whole bunch of different values. You can see that here we have 0 angles of attack, and that corresponds to a lift coefficient of 0.2 and a drag coefficient of a little bit less than 0.2. And as they increase the angle of attack, you can see that lift goes up, but so does drag. So these are known as drag lift drag polars or drag polars, something like that. This is sort of one way of just visualizing the data instead of plotting it with respect to angle of attack. So at the high end of this, you get a lift coefficient of 0.08. So the question that this literature was focused on, including the study from 1990, is just this, is this lift coefficient sufficient to support the mass of the animal that I'm interested in? So that's the question I pose to you. So with the time left, see if you can answer that question. And I haven't handed you cards. Let's just do it. Let's just do it without the cards today. So, so just hopefully you guys on your. Does anybody need something to write with? No. Okay. So just try to do the calculation without the cards. Okay, I'm giving you some parameter values here.
Yeah.
Does anybody have an answer? Okay, I'm gonna have to cut it short because we're running out of time. Sorry. Okay, but like with all of our problems, the crux is really setting up the problem correctly. So here, what you want to do is set up a force balance that the weight is equal and opposite to the lift that's being generated by the wing. And then it's just a matter of sort of plugging in the values, the parameter values that I finally gave you. And what you see is that the mass that could be supported by this level of lift is 0.3 grams or 300 milligrams. And that's at the best angle of attack. So that's like the best case scenario. We're still 300 milligrams below what we need in order to actually fly. So this is known as the bumblebee paradox. It's an idea that biologists were grappling with for some time. And the question is, why is it that standard aeronautical engineering, which is what we have employed here, does not explain how a bumblebee or any insect can fly? And so that's the paradox, and I'll explain it next time.